All right, my friends, so for the last video in this series, I want to walk you through some of the most common derivative rules that we're going to use. As I mentioned before, in this class we're going to take a lot of derivatives, but it's really going to be the same derivatives over and over. So if you get comfortable with using these rules and combining these rules with each other, you should be in pretty good shape when it comes to taking derivatives. So there's really just a couple things that we're going to do. We're going to take derivatives where we have a variable multiplied by a constant. We're going to have derivatives where a variable is added to a constant. We're going to have power functions. We're going to have log functions. We're going to have chain rules. So I'll go through each of these in turn. So first we're going to have, let's start with addition. Variable added to a constant. Right? So we might have, for example, something like f of x equals x plus some constant n, right? So this could be, for example, x plus 3. It could be x plus 5. Yeah? Okay. So the general rule here is that when we have a constant added to our variable, we take the derivative, the constant disappears. The reason that this works is, let's graph these two functions I have here, right? X plus 3 and x plus 5. So if I have x and I have f of x, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? So, okay, if I'm going to graph x plus 3, when x is 0, f of x is going to be 3. Right? When x is 1, f of x is going to be 4. When x is 2, f of x is going to be 5, etc., etc. Good? Okay. How about x plus 5? Well, when x is 0, f of x is going to be 5. When x is 1, f of x is going to be 6. When x is 2, f of x is going to be 7. Yada, 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 right? F of x equals x plus 5. Okay, great. So if we're thinking about the rate of change, right? If we're thinking about the slope of these two lines, you can see that these two slopes are identical, right? If x goes up by 1, both of these functions go up by 1, right? Let's say that I started at 2 and went to 3, right? I'm sorry, if I started at 1 and I went to 2, right? With this function here, I would go from a value of 6 to a value of 7, plus 1. If I started at 1 and I went to 2 with our blue function, we would go from a value of f of x of 4 to a value of 5, also plus 1, right? So we can see that the constant here doesn't matter. And so that's going to be our general rule. The f dx is just going to be x, right? Plus 0. The a goes away. Okay, good? So that's what we do with addition. How about multiplication? So for example, we could have, or in general, we could have f of x equals a times x, right? Where a is just some number. So we can have as an example, f of x equals 2x, or f of x equals 3x. Okay. So what do you think? Is it going to matter whether we have, for the derivative, whether we have a 2 or a 3 in front of x? I'm going to say that in this case it does. So let's do the same thing. We're going to graph our functions. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I got it, right? Okay. So if I graph f of x equals 2x, when x equals 1, f of x is going to be 2 times 1 is 2, right? When x is 2, f of x is going to be 4. When x is 3, f of x is going to be 6. Agree? So we're going to have a line like this. Okay. What am I doing? We're not going to have a line like that. When x is 0, f of x is going to be 0, right? We're going to have a line like this. Okay. Good. Okay. How about our red function, where f of x equals 3x? Well, when x is 0, 3 times 0 is 0. When x is 1, 3 times 1 is 3. When x is 2, 3 times 2 is 6, right? Et cetera, et cetera. So what we can see is our red line is steeper than our blue line, right? This means that a 1 unit increase in x increases f of x more on our red line than on our blue line, right? If we take an example, let's say when we go from having x equal to 0 to x equal to 1, we're going to have an increase on our blue line of plus 2, increase on our red line of plus 3, right? So we can see that it matters. We can also see, well, what's this plus 2 and this plus 3? It's just these constants, right? So our general rule is going to be f of x equals a times x, then df dx is going to be a, okay? So, right, our blue derivative is going to be 2, our red derivative is going to be 3. Okay, good, good. Okay, so these are our first two rules. Our third rule that I want to talk through is our power rule. So what I mean by our power rule, or power functions, is functions where we have a variable to some power, right? So this is going to be, for example, f of x equals x to the a in general. We could have as a couple examples, let's say f of x equals x squared. And to throw a curveball at you, right, let's start combining our rules. So I could say f of x equals 3 plus 2x to the 1/3. Okay, good. So in general, our rule is going to be, and this time I'm not going to justify it as much, right, because it gets harder to show this easily. But our rule is going to be that the derivative of this sort of function is going to be a times x to the a minus 1, right? So that is the power that we have x to. We're going to lower the power by 1. We're going to multiply the derivative by the power itself. Okay, so for example, if we have f of x equals x squared, we would say the derivative of f with respect to x is going to be 2 times x. Yeah? Okay. If we want to sort of justify this a little bit, right, without going full epsilon delta proof and spending a lot of time on it, we could very quickly graph this. Just to note, right, that if we have something like, well, if x is 0, then x squared is 0, x is 1, x squared is 1, if x is 2, x squared is 4, when x is 3, x squared is 9. Yeah, so we're going to have a shape sort of like this. Okay. So what do we notice about this graph? What do we notice about the shape? Well, we can notice that going from x equals 0 to x equals 1 adds 1. Going from x equals 1 to x equals 2 adds 3, right? We go from 1 to 4. Going from x equals 2 to x equals 3 is going to add 5, right? Bringing us from 4 to 9. So I'm reluctant to show you this because these numbers don't exactly fit our formula. The reason for this is that this is going to tell us essentially a change over a big range of x's rather than the rate of change at a specific x. But at the very least, what we can see is that when we have f of x equals x squared, right, our derivative should be getting bigger and bigger as x gets bigger and bigger. And that is what we're seeing, right, is that if we have higher values of x, 2x is also bigger. It means that x squared is increasing faster. Okay, good. So let's do a slightly more involved example where we have f of x equals 3 plus 2x to the 1/3. And let's remember all of our rules. Okay, so what's the f dx? Well, the first thing we can do is we can say, what do we do with that 3? Well, as we talked about before, right, this is going to be a constant added to a variable. Right, in this case, a variable with a bunch of stuff done to it, but the basic intuition of this constant is the same. Right, if this constant was 5, shift the whole function up. So that's going to become 0. Then I have 2. That's a constant multiplied by a variable. So that's going to stay what it was. And then I have x to the 1/3. Right, so what am I going to do with that? Well, now my value of a here, right, my power on x is going to be 1/3. So I'm going to bring down the power and I'm going to take x to the 1/3 minus 1. Make sense? So what this is going to do, right, we can simplify this. We can say 0 plus 2 times 1/3 times, what's 1/3 minus 1? That's going to be negative 2/3, right? Right, and if we want, right, something to a negative power is the same as dividing by the value to a positive power. So this could instead become 2/3 times 1 over x to the 2/3. All right, beautiful. So that's our power rule. Okay, so next up we've got log functions. This is generally going to be, this is pretty much always going to be, for our purposes, the same function, which is just going to be something like f of x is going to equal the ln of x. Right? The only variations, we could have like 2 times the ln of x, or the ln of x plus 6, or something like this, but we're basically always going to be taking the natural log of x. Okay, so our general derivative here is going to be 1 over x. If I had, let's give you a slightly more complicated example. Let's say I had f of x equals 3 ln x, right? Then our derivative would just be using the multiply by a constant rule before, 3 times 1 over x, right? Or if we prefer, 3 over x. Okay, so I want to talk very briefly about how to remember this rule, right? Again, without doing an epsilon delta proof or anything like that. Just thinking about why would this rule make sense. And to do that, even though we were talking about natural logs here, I'm going to talk about log base 10, because that's a little bit easier for us to think about. So if I had log base 10, essentially what this means is that f of x here is the power you need to put 10 to in order to get x, right? So we would say, let's make a table of x versus the log of x, right? We would say that if x equals 1, well, 10 to the 0 equals 1, so the log of x would be 0. 10 to the 0 equals 1. Annoying. If x was 10, then the log of x is going to be 1, right? Because 10 to the first power equals 10, right? If x was 100, the log of x is going to be 2, right? Because 10 squared equals 100. And if x was 1,000, log of x is going to be 3. Because 10 cubed equals 1,000. Okay, this makes sense? This looks familiar? So the point here is just, if we think about the change in x versus the change in the log of x, what we can see is that as x gets bigger and bigger, it takes a bigger and bigger change in x to get a change in log of x, right? Going from x equals 1 to x equals 10, I added 9 to x, I added 1 to log of x, right? So the slope here is going to be something like 1/9. When I go from x equals 10 to x equals 100, I added 90 to x, only added 1 to log of x, right? So what this should tell us is that the rate of change, the amount that f of x increases when x increases by a little bit, should get smaller and smaller and smaller as x gets bigger and bigger and bigger. And that's exactly what happens if I have a derivative like 1 of x, right? Increasing x continues to increase the log of x. It's just incremental increases in x change log of x less and less and less. Okay, so that's our log function rule. Then the very last thing I want to throw at you is our chain rule. And this is essentially a rule about what do we do when I have one function inside another function. So the general rule here is going to be if I have something like f of x equals 2 functions, let's say h of g of x my derivative is going to be the derivative of g with respect to x times the derivative of h with respect to x time evaluated at g of x. Okay, so this is super complicated. Writing it out like this is not very helpful at all. So let's go through a couple of examples, right, to remind ourselves what we're doing. So let's say that I had something like f of x equals two x plus 3, the quantity squared. So what I have here is, right, a function here, 2x plus 3, and another function, x squared, right? So I would say essentially that using this terminology, I would say h of x is 2x plus 3, and g of x equals x squared, right? So using our rule, I would say, well, the derivative of h with respect to x, derivative of 2x plus 3 is just 2, right? The 3 goes away, multiplied by a constant. Derivative of g with respect to x is going to be 2x, right? Derivative of x squared with respect to x. Okay. So that's going to tell us that the derivative of f with respect to x is going to be 2 times 2x. Okay. You see how I'm doing this? So in order to make this make sense, I'm actually going to make this a little bit simpler. I'm going to make this into a problem that we could solve using the chain rule, but that we don't have to solve using the chain rule. So let's say instead that I'd given you that f of x equals 2x squared. Yeah? Oh, I'm so sorry. This 2x here, my goodness, what am I doing? This should have been 2 times 2 evaluated at g of x. So it should have been 2 times 2 x plus 3, 2x plus 3. Yeah, so then this is going to end up becoming 4 times 2x plus 3. Okay, anyway, back to this problem, right? Where I make this even simpler, I'm going to say just f of x equals 2x, the whole quantity squared. If I did this without the chain rule, right, all I would do is I could say, well, this is the same as 2 squared times x squared, right, which is going to be 4 times x squared. Now we have a simple power function, so I can say that the derivative of f with respect to x is going to be 4 times 2x to the 1, right, or 8x. Does this make sense? So this is the answer we should get. But we could also think about this as being a function inside a function, right? One function is h of x equals 2x. The other function is g of x equals x squared, right? Then what we would do is we would say, well, the derivative of h of x with respect to x is going to be 2. Derivative of g of x with respect to x is going to be 2x, right? And so this is going to give us df dx is going to be 2, derivative of the outside, times the derivative of the inside, evaluated at h of x, right? So 2 times 2 times 2x, which is indeed going to be 8x. Okay. So what I'd recommend if you're stuck on a chain rule problem, right, and if it's not coming easily to you, is just go back to something like this, right? Go back to something like 2x squared. Use the procedure that you're trying to use for a more complicated problem. Make sure that it gives you the right answer, right? If you end up doing something, making a mistake like the mistake I made, right, where you forgot to plug in the value of h of x into your g function, right, then you're going to notice it when you get the wrong answer on a question where you know the answer. Okay, so to summarize, right, this is essentially all of the calculus we're going to do in this class. You've seen all of it. So if you're able to get comfortable with these couple of derivatives, you should be smooth sailing in terms of calculus. All right, thank you so much. Don't hesitate to ask me any questions or let me know anything that could be helpful.